One of the first things will be what they call all plastic belting. All plastic belting is an extrusion. And we're going to talk about a couple of different types of plastic today. This one happens to be an extrusion. We run it through an extrusion head. It's extruded in different lengths depending upon what the manufacturing setup is. It comes in either a flat or a profile. Now, a profile in this case is not something on the surface of a flat belt. In this case, we're talking about a profile being something like this, which is a round belt, or possibly something like this, which is a V. Okay? So we're talking about rounds and Vs. We'll talk a little bit more about that in a minute. But this is what an extrusion is. In this particular case, we've got some application pictures in a couple of these. Compound-wise, when they do the extrusions, most of the compounds are going to be some form of polyurethane, either with some type of adders in it or a derivative of polyurethane. There is also an extruded polyester. This is the harder material. So when you hear people refer to something that's a hard all-plastic extrusion, generally it's going to be either a urethane with an adder in it to make it harder, or a polyester. Polyester bonds differently. You've got to be careful when you start talking about polyesters. Flat belt. Notice this is one of the pictures that doesn't necessarily go with the verbiage. Flat belt is just like we talked about yesterday. It's extruded in a certain width. Most of them are extruded in either 72-inch or 60-inch widths. This is not easy to come in and do a longitudinal, so don't be looking for an 84-inch wide version of this because it's much more difficult to do. And when we do an extrusion, it's generally what it says it is. It's an all plastic. So we get things like this. In this particular case, this is polyurethane. Okay? As you notice, it is an all plastic material. If you can take that and pass that back, please. That would be the polyurethane. This is a polyester version. As you can see, this came off the end of the roll because it's curled a little bit. If you take one of those and pass those back, please. They are done, they will have different designations to tell you kind of what the hardness is and so forth. From a standpoint of stretch, let's talk about stretch since we were talking about load. One of the things you will notice on this is there is no tensile member. So these will stretch a little bit more. In a lot of cases, they'll do what they call pre-tension. Now, when Dan talks about nylon core later on, and we talk about how some of this stuff is used for transmission applications, you pre-tension a lot of the transmission applications. Same thing with this. You may want to pre-tension it to take some of that preliminary stretch out of it so that when it goes on and they tighten it up, some of that's already gone and they're not going to extend it out beyond the take-ups. That will vary depending upon what the manufacturers tell you. Ask. There are data sheets on this, and it will tell you on the data sheets what to factor in for pre-tensioning for the different materials. Comes in different thicknesses. You can get things down as thin as 1.5 millimeter thick all the way up to 5 millimeter thick. For those little challenged with millimeters, that's a little under 1/4 of an inch as far as the thickness is concerned at the top end. Now, you can do some other things with it as far as thicknesses are concerned. For example, if somebody wanted to make a narrow belt and put two 5 millimeter pieces together, you can do that. But then your pulleys are going to go up appreciably as well. All of this has minimum pulley diameters and everything else, just like everything we talked about yesterday. On occasion, in order to get the benefit of the surface, but eliminate some of the stretch problems, they will put a fabric backing on it. This is a single ply polyester monofilament. Has a 6 Newton rating in most cases. Some of them do 8. Everybody remembers how to convert that, right? How do you convert it? 5.6? See, I told you it was going to be a test. All right. This happens to be for, when we talk about industries later today, you'll see this one come up. They also do this in a food grade. This is a non-food grade version for general industry. And what you're looking for is something that'll wear, give good abrasion resistance. This has a 3 millimeter thick top cover on it, which is heavier than most will be. And if you'd pass those two back behind you.
1.5 mil is about 68 thousandths, and so 3 would be closer to an eighth.
59.
One of the things you have to pay very close attention to, notice how slick this is. So pay close attention to your drive pulley lagging.
Okay. Tell them what lagging is, because we didn't talk about lagging.
Oh, we talked about lagging yesterday.
Briefly.
Yes, we did.
Briefly.
We did.
Okay.
So I made sure we talked about lagging. So I think about lagging because ultimately we have to power these drives. Otherwise our belts go nowhere. So, so in this belt, if you don't pre-tension it, it will not track and it will not run straight. So it does need some tension on it, not over tension, just proper tension. So pay attention to your lagging, make sure your lagging is good. When you put on a new belt, makes sense to put on new lagging. Yes, Roy?
Many times on that style of belt, you'll have a knurled drive pulley, just as a means of driving it. And you know what a knurled drive pulley is?
Yeah, it's something that cuts up the bottom of the belt.
Yes.
So make
And we
sure
love
that,
Yes.
so make sure that it's appropriate. Okay. You don't want to overdo it. It's very easy to take and cut a diamond pattern into a piece of steel on a lathe, and yeah, you can just chew up the bottom of that belt and make a big mess.
Hopefully
So-
it's done right with
Yeah.
some kind of a pebbling type surface or
Yeah.
Very
And
wet
very-
conditions,
very-
though, I think knurling is probably what you see more often than
Yes.
anything in the meat plants.
yeah,
for sure.
absolutely.
Yeah. Yeah. So they can clean it.
Right.
But be careful with your knurl, depth of knurl, and your knurl pattern.
V's and rounds, we talked about those as well. There's pizza, our favorite topic. So you can do these in different durometers. They do them in different colors. They'll do them solid extrusion. They also do these with a reinforcement in them on some occasions, so that if you've got heavy loads or anything else, you can put those together and make it work so it doesn't stretch as much. Again, you're going to have stretch factors in with these, so you're going to probably pre-tension a lot of this. Now, as Chip mentioned, there was a positive drive version of this. If we want to cut down on the amount of slippage and get something that has more reinforcement similar to a plastic modular belt, runs on drive sprockets and so forth, you do something like this. This is an extrusion, but now we've added teeth to the bottom of it. There are people that will turn this over and run it as a profile up to carry a product for separation purposes or whatever, but for the most part this is used on a drive sprocket to positively drive a belt. It runs at less tension. Here you're only talking about maybe up to 1/3 of 1% tension, as opposed to most of the others that are going to run somewhere between 1/2 to 1 or a little better. I'll pass these around. There are several different manufacturers that do this, and there are several different variations. That happens to be the most common one, which is on a 2-inch pitch. Now when we talk about pitch, what we're talking about, and we'll do the same thing on modular, you're talking about from the center of one tooth to the center of the next tooth. That's what is referred to as the pitch of the belt. This happens to be 2 inches nominal. This one is about 3/4 of an inch nominal. Runs on a drive sprocket. The big thing with this is sanitation and cleanability. If you're in, we were talking yesterday about the meat and the poultry, and we're going to talk some more about meat and poultry in a little bit. The reason this is becoming so successful is because it's much easier to clean, lower bacteria counts, less time, less water usage, less chemical usage. There's a whole raft of things here. And we talked yesterday, I know it was mentioned about bringing value to your customers. This is one thing you can do to bring value, because what you're trying to do is reduce their overall costs of operation. A little different sales gimmick, but that's it. There's also this version out here. There's a couple manufacturers that are doing this. Instead of having the tooth all the way across, it is centered on the belt. So it would run on something like this, or a flat tooth on here. There's different sprocket styles and everything for all the different versions. But that would be positive drive. Again, this shows round belt on it, different applications. They run loose so they won't stretch. What you're trying to do is take the stretch out of here. These were made to compete with modular plastic, pure and simple. Okay? So modular plastic runs loose. It has catenary sag. The big problem with these, if you tension them up too much and they start to stretch, they get out of pitch and they will jump the teeth of the sprocket. So all we're trying to do is keep everything in pitch as it runs around those sprockets. Otherwise, what will happen is it'll engage with a couple of teeth and then it's going to hop out. All you're trying to do is, again, get this somewhere in that 1/3% range as far as the tension is concerned. You don't need a lot of sag, and depending upon the conveyor, your sag may be in one place coming off the drive sprocket, or it may be in multiple places in between rollers on the return side. All right, so these are the positive drive versions. You'll notice the samples we sent around are in blue. Most of this stuff is made in blue because how many blue foods do you know? Not a lot. And in the food industry, they're looking for contrast. They're looking for something they can pick up readily easy. Other than a blue M&M, there's not a whole lot of blue stuff out there. Accessories, can you do cleats and all this stuff on these? Absolutely. Cleats can be done a little differently. First off, you can use, we talked yesterday about T-cleats. You can do T-cleats, you can do angle cleats, you can do scoop cleats. It has to be a common material. You can't turn around and try to bond a polyester to a polyurethane. You can't bond PVC on any of this. So it has to be a like material. In some cases, what they will do, if I can borrow this and one of those other samples, please. In some cases, what they will actually do, instead of taking a T or something like that, if you want to get something that's heavier, you may take a piece of 5mm flat stock, turn it on its edge, and bond that to the surface of the belt to get something heavier. There are actually cleats out there in use today that have had several pieces of material fused together to form a 3/4 inch thick cleat to push 80-pound frozen blocks of beef on it.
And they'll also add a gusset to the back of that cleat to reinforce it.
Know what a gusset is?
That's what I was wondering.
Gusset is a reinforcement on the back that's attached to the cleat, not necessarily
the bottom.
attached to the surface, because when it goes over the pulley, you want that to be able to lift up and still flex. And that gives it some additional support when it goes over, okay, as far as pushing some heavy loads. Gusset. Yeah.
Yes. But just keep in mind that it is only attached to the cleat itself, not to the base.
Yeah.
You want me to draw a picture? Or would you like Roy to?
Same material.
Same
Same
material.
material, like material.
Same material.
Would be like material.
It's always got to be these same materials.
It's fastened.
If you use dissimilar materials, they won't adhere to each other.
Draw them a picture. Keep it about 1/8 of an inch, roughly, off the base of the.
Okay. So you'll get some deflection this way.
And depending upon the width, you may have multiple gussets
Yeah.
placed on that cleat, depending upon the load that you're trying to carry.
Roy didn't think I could do that.
I knew you'd do a better job. You're an engineer.
There's no real air gap here. I just did that to illustrate that it kisses but is not bonded. So it's just not bonded. You bond here, and this you do have a little fillet here, a little fillet on the backside.
You will have the need to have something underneath that as you're applying it to your gusset in order to put it on. So you'd have some kind of a spacer, a shim underneath the gusset itself as you're applying it to the back of the cleat.
All right, you can also do V-guides with this. I mean, you can take, again, similar material, put a V-guide on the bottom side if you want to help assist in tracking. You can put the guides up on top as the spill edges that we talked about yesterday. You can put guides across the surface of a belt to form lanes if you want to have something that'll create separation and everything else.
Just back up a quick sec. You're better off to prepare your cleat first with your gusset in place and then weld.
Depends on the tool you have to
Yeah.
put the cleat on.
Yeah.
There many times you don't have that luxury of being able to apply it and then be able to apply your cleat.
ask your boss for another tool. It's a better way to do it.
You can also perforate. Now we're going to give you a word of caution here on perforating. Yesterday when we talked about perforations on belts with fabric reinforcement and everything, we said it's going to reduce the amount of load capacity, it's going to weaken the belt. When you take something that has no fabric in it and start putting holes in it, which this already stretches before you take some of the material out of here, you've got to be very, very cautious as to what your hole patterns are, how much open area you're going to end up putting in here and everything else. So generally, even though we do perforate some of these, in most cases it's going to be the type with the fabric reinforcement, or it's going to be one of these with the positive drive option. There's several different methods of perforating. The cleanest is either a laser or a water jet. Those are the two best ways. Otherwise, you could do it with a standard clicker press and a die. There's an automated punching equipment that's out there. Don't recommend for any of you guys, and I know it's difficult to spend money on equipment and everything else, but to stand there with a simple die and a hammer is not the best way to put holes in a belt. Okay?
Drilling is a little messy, but
Drilling's a little messy. So the best way is to get somebody that's got the right equipment to do it, especially if you've got a lot of holes in it. Especially if you've got a lot of holes.
Yeah, drilling actually bores the material and creates the thing. That's your last choice.
Yeah.
You really don't want to do that because it doesn't make a good hole. It's going to be a very irregular hole. Best thing is punch and die. Punch and die.
and holes in a unsupported thermoplastic really weakens its load carrying
Big time.
capability, much more so than a belt with fabric in it.
Yeah. Well, and that's why I said most cases you're going to do it with a fabric reinforced base on it or the positive drive versions. Okay. Splicing wise, the old style system that first came out, they used to take a piece of electrode, which was something similar to this, and they'd run it through a special nozzle on a Leister gun, and you'd put the two ends together and melt the electrode and the two ends of the belt all at one time and fuse it together. You had to know what you were doing, and you had to have the feel or the touch to know when this was melting and fusing. If you did not, you weren't going to get a good bond. As simple as that. And many a time, I'm sure we've all seen somebody go ahead and do that, put a little tension on the belt, and it just goes, pulls right apart.
Splice looks good,
Splice looks great,
but it
but
isn't.
it's not going to hold. So they still do that in certain cases, but the big method right now is to butt weld it. If you've ever seen any of these put together, you take a little tool that's got a Teflon tipped heater on the end of it, melt the two ends, push it together, you get this little flashing that comes out, that's your melted area. Don't push it too hard, because if you squeeze all the flashing out, now there's nothing there to hold it. And we do the same thing with the flat belt. Just, it's a bigger wand, you melt everything together, push the two ends together, let it cool. Takes about 5 minutes to get it back down to room temperature. That handy dandy little tool that Tom showed you yesterday, in addition to doing lacing and being able to strip rough top off, does a great job of stripping off the flashing on here. Run that right across there and it'll take it right off.
By the way, I was in one of your locations about 2 years ago, and somebody had a barrel that was, let's say it was a 35-gallon barrel, and they must have had about 3 feet deep of these things. You can actually sharpen them, you know. I was astounded. It hundreds of these things, and you can resharpen them with a simple little diamond hone. So keep them sharp. Keep them sharp. They will take a fraction of the time and do a much, much better job. Rubber by its nature, even PVC and urethane, wants to yield and move around on you. If you keep it nice and sharp, you'll just go right through it easy.
Yeah.
Speaking in generalities here, this always helped me to understand when you were splicing unsupported thermoplastic. Thermoplastic, urethanes, polyesters reach a point where they want to melt, and you see that as a sharp peak. It's not a slow curve or not a slow ramp. In other words, it doesn't, and I'm speaking in generality, it doesn't necessarily start out like bubble gum, turn into motor oil, and then water when it comes to viscosities. It kind of stays in a certain state, and then it hits that spot where it wants to melt all at once. When it hits that spot, the viscosity, based on your cooking temperatures and everything, is right for those two pieces to flow together.
And if you don't want to do that, you can put fasteners in this. Now, we recommend, generally speaking, and this is an industry recommendation, not mine, that you use a rivet type fastener because you get more bite in here, especially when you don't have any fabric to hold anything. So you get more bite in here with the rivet type fasteners, whether it's a plastic or a metal rivet fastener, and that'll hold up fine. These belts weren't designed to have fasteners put in them. They were designed to be spliced endless for cleanability and sanitation. Okay?
Okay, we're going to talk about another style of lightweight belting that you'll see out there. The first category we'll talk about is called quick splice tapes. And the quick splice tapes is a style of high-speed, thin conveying belt used in the printing industry primarily that is called quick splice for two reasons. They are melted together. You have two styles. You have one style that has a polyester core, just much like your unsupported thermoplastic belting, and that polyester core can be melted via a finger splice. So you would put the fingers, you'd cut the fingers in it, you would put it together, you would put it in a press, and you would melt the polyester in the middle to get your splice. Now they'll take that polyester core and cover it with all kinds of materials depending on what you want to convey. Generally speaking, you'll see a quick splice tape covered with a rubber of some kind, an NBR rubber, or a textile fabric of some sort. Again, depending on what you want to convey. If you want grab and you want to make sure you're positively moving a product through something that's printing it or stacking it or assembling something, you would want to use the rubber top on that quick splice tape. If you want something that's a little kinder to the product and maybe not mark it or tear it up, you would use a bare textile cover on the top. The primary reason, though, for the polyester is indeed to be able to splice it quickly compared to the other style of belt that you might see that we'll talk about in a minute called nylon core. So polyester has some distinct advantages as well as being able to splice quickly. You don't need to use, I'll say the word adhesives or catalysts to get a splice. It's basically done with heat. It is non-hydroscopic like nylon might be. So it doesn't have a tendency to absorb moisture like nylon would. Some of its drawbacks may be it's what we call shock load capacities. Polyesters, when they receive a shock load, in other words, a guy's planing a piece of wood, it hits a knot and that belt's trying to pull and it can't. That belt will stretch out to a point. Polyester will not come back to its original size like nylon core might. So it's generally used in thinner, narrower pieces for high speeds. When it comes to jam-ups and things like that, it will stretch to a certain point and then go beyond the point of it wanting to come back. Disadvantage. Advantages: it's non-hydroscopic, not affected by humidities and things like nylon core would be. It splices quickly, and you don't have to use anything other than a hot press to do it. Those are the advantages to quick splices. There is another one that I would put in there in that category, and I'll send some of this stuff around, that would, in my mind, be quick splice as well. But it is unsupported. In the industry, we've always called them stretchy belts. Okay, the belts stretch. They're meant to stretch, and those are put on systems that have common shafts without take-up. So you would cut the belt short, put it on, and they would all, you wouldn't need exact dimensions to be able to run them on the same shaft, because they stretch on, they conform to the size and the shaft. We call them stretchy belts. You preload them with a certain amount of tension to get them to run and carry the loads. But you see stretchy belts a lot of times, and you'll see some of our application photos where they have all kinds of pulleys and back bends and things going on in there. They don't have room or don't want to spend the money on an awful lot of take-up or tensioning devices that might be spring-loaded. They can get the tensions by cutting it short, putting it on, and letting the stretch of the belt handle the take-up that it needs to pull the load. So I'll send these around. On there you will see too a nylon core belt and a polyester quick splice type belt look an awful lot alike. What they do is they take a piece of polyester and they actually bond rubber, or they bond the textile to the polyester. Some folks will take that polyester and, to give it more integrity, embed a fabric in the middle of it, just like these styles might. Again, to maybe give it better shock load characteristics or a better ability to pull a higher load, you'll see some folks putting a reinforcement in that polyester. But they bond those things together under heat and pressure. There are probably adhesives being used when you do that under heat and pressure to get those bonds to have integrity. It's not often easy to bond rubber to plastic, so there are techniques that you have to use to do that. Thermal plastic core. That's the that's the polyester we're talking about. A variety of covers, anything from fabric to rubber to even polyurethane on some of these things. Generally finger spliced, but you can butt weld, and that's the stretchy belt that we're talking about there, being able to butt weld that one. Fingers may vary on the style and type. Special welding tools are used to get a high tip bond quickly. And again, on the stretchy belt, we're talking about the same kind of tools that you would use basically to melt these. You put a wand in the middle, you heat the ends up, you push it together, you have a bond. They can be finger spliced as well. Typically you see people use the wand and a butt splice on the stretchy style of belts. On the polyesters that are covered with rubber or fabric, those will be finger spliced. You don't see those butt welded. Those are pretty much always finger spliced. And the reasons for using that style of belt is ease of installation. It's user friendly because you don't have to worry about adhesives or catalysts to get a bond, and it reduces the downtime. It's faster to get a belt on the machine and get it up and running and all that kind of stuff. So that's where you would see and why you would use a quick splice. The other style when it comes to high speed, and we can talk very high speeds here with nylon core. Nylon core is a belt that has, like it says, the core is made of nylon. Not polyester, not urethane, that is a nylon. Now nylon is a kind of plastic as well. But it's used again for very high speed conveying and power transmission. And we're talking power transmitted on lathes or punch presses or things where you need to transmit power, much like a V-belt would. You'll see nylon core doing that. So I'll talk a little bit about tensioning. It's real important. Nylon core has a very low stretch for its weight. It's a high strength to weight ratio. So very narrow nylon cores can transmit an awful lot of power for the actual weight of the belt. It's very good for shock loads. When I was talking about the polyester hitting a shock load and then stretching out to the point where it can't come back, nylon will hit that shock load, stretch out, and come back to its original shape much better than a polyester core will. Much better for shock loading. It has a very good memory. It comes back, it returns to its original shape and size. Nylon core has a variety of covers available, much like polyester. But let me tell you a little bit about how it's actually made. Because it is difficult to get rubber to bond to nylon, it has to be done in several layers. So what a person will do is they'll take a piece of nylon. I'll pass these around in a minute, but you'll see the nylon looks black. It's actually clear when it starts out. That nylon is a clear color. And what we do in the industry is we would take that clear nylon and a piece of fabric that is a nylon fabric as well. You take the nylon fabric and you treat it and you coat it and you do things to it, and then under heat and pressure you impregnate that nylon with rubber on one side. So you're forcing the rubber into that nylon and the little holes in the weave and all that kind of stuff that's been treated and heat set and all that, and you're forcing rubber into that piece of fabric. And what you're doing there is you're creating two surfaces. The bottom surface is nylon and the top surface is rubber, and it's all fused together. And the reason for that is you would take that nylon then and you would put the nylon side on the nylon, hit it with your catalysts and things that would actually melt the nylon through a chemical process, and then that nylon bonds to the nylon, and then you have a rubber surface on top. That's where you bond the rubber to. So you have to go through several layers and processes to make this stuff, and then the rubber then would use catalysts as well, and under heat and pressure we take that sandwich of nylon to nylon, rubber to rubber, and put it under heat and pressure, bond it all together, and that's how you build a nylon core belt. A little bit different than how you would build the polyester cores and quick splices, as it is difficult to get rubber to stick to plastic, and it's done in multiple layers. So covers available, and this is pretty much true of the finger spliceable stuff as well. Here again, I was talking nylon fabric. You can put nylon fabric on these covers. You'll see a variety of styles and types in here. Rubber bonded to the top, rubber bonded to the bottom, rubber by rubber, textile by rubber, rubber on one side, textile on another. All kinds of variations of that, again, for the specific application. Whether you're folding a box, whether you're printing an envelope, on and on and on. Wherever paper is involved, you will see nylon core. Fabric used on the top and the bottom, it produces a slick, soft surface, as you can imagine, to avoid damaging delicate products. Tissue paper-like products that are being printed or folded or something like that. You also see another style of nylon core that's been around for a long time, and that's leather bonded to the top and the bottom. You primarily see leather on these in power transmission applications, where the leather is used to transmit power, but it's a fail-safe device for very large shafts. And if there was a jam-up or a catastrophe of some kind, you would want the belt to slip rather than to bend a shaft or screw up a gearbox or something like that. So in the old days, a lot of people used quite a bit of leather as a fail-safe device on their heavy equipment when it came to transmitting power. In other words, applications where slippage will limit torque and protect the machinery, right? So this comes in various sizes and thicknesses. The strength of a nylon core belt is determined by the thickness of the nylon core and the width of the belt. And there's a direct relationship in percentage of strength. So the wider it gets, if it's 1% wider, it's 1% stronger. If it's 1% thicker, it's 1% stronger. So nylon core's strength is entirely in that nylon core, and that's determined by the thickness of the nylon core and how wide the belt is. So in practicality, as you apply nylon core, you can get the belt stronger by going to a thicker nylon, or you can get the belt stronger by going to a wider belt, depending on how you want to use it and what's most competitive and if you have the room. Either way will get you a stronger, heavier load carrying capability when it comes to nylon core. Splicing. Let me talk a little about tensioning though. With nylon core, because it has a memory and we do use it to transmit power so many times, pre-tensioning that belt is very, very important. That's something a lot of people really overlook with nylon core in particular, is pre-tensioning that belt to get it to pull the load. you may have to put several percent, 1, 2%, sometimes more, on nylon core belts to get them to pull the loads and to accept the shock and still come back to its original shape. I give you an example. A quick one would be a line shaft in a paper mill. They have cone drives, they're called. These drives have a very heavy belt that wraps around them on a big shaft across the top that drives multiple units as they're making paper. They're called cone drives. And the cones adjust the speed of the equipment as they move in and out. With all of that power that's being transmitted through multiple belts on these paper making pieces of equipment, you might take a thick a belt like that, 5 millimeter, sometimes more on the thickness of the nylon, and you might have to stretch that belt or pull it 10 to 12 inches to put the splice in before you're going to be transmitting the power necessary to power that equipment. Now, stretching a belt that thick, that much, you're probably in the neighborhood of 4,000 to 5,000 pounds of pressure that you're pulling that belt to get that to stick together and transmit that power. That's a lot. Very dangerous installation, to say the least. You have come-alongs, and you're cranking that belt, and you're ratcheting it closer and closer together so you can put the press on it and stick it together. And that's where the splicing always amazed me, because when you splice nylon core, let me draw this for you. You have the belt like this, and let's look at the edge of the belt. That of course is much thinner. And we're talking about a skive splice, right? We talked about that yesterday. The skive here would be the other way, right? So that the two ends meet, the thickness of the belt is maintained, right? When you skive these belts, what you see when you look down at them widthwise, this way, is you'll see a certain amount of the rubber on the back side of that belt will be exposed. This would be rubber, okay? Then you'll see another place, and this will be nylon. And then this again is rubber, okay? So when you skive the belts, when you skive a nylon core and you're putting it together to get it to carry a load, the two ends have to match. In other words, this won't be the right dimension, but this is the other part of the belt. This belt's going this way. This is the other end of the belt, where you have, again, the rubber exposed, you have the nylon exposed, and then you're back to rubber. This nylon and this nylon has to match up because that's where the strength's at, right? So what you do is you use a catalyst. It's not an adhesive, it's not a glue, but with a chemical process, the catalysts melt the nylon to the nylon. So when we do these splices, it's very, very important that you do things like match lines. Match lines on this belt, so you know that this end comes up to the match line so that you have as much nylon to nylon contact when you put those two ends together as possible. It's very important. A little bit can make a big difference because we're not talking about a whole lot of size there. The splices can be very small in relationship to that belt. But you have to use a match line so that you can make sure that the nylon matches to the nylon. You use your catalysts in there which melt the belt under with a chemical process, and then that process is sped up and helped by putting it in a press. The heat does not melt the nylon, it just accelerates the catalyst to get the bond. The pressure also helps when it comes to getting these things to stick together. I can't emphasize that enough. Nylon to nylon, that's where the strength of that belt is. Yeah, right.
Make sure we have to make sure that none of your adhesive gets on the nylon. And you have to mask it off or do something to protect that nylon as you put your adhesive down. Because if you get any of your adhesive on the nylon, it's going to affect that ability to bond when you put the catalyst on.
Good point. I'll fine tune this a little bit.
Okay.
You're talking about adhesives now.
Right.
When you put these two things together, it's very likely, depending on the belt, that you would use a nylon catalyst
Yeah.
for the nylon,
Right.
and the rubber part you would stick down with an adhesive.
Right.
That is truly a glue,
Yes.
okay?
And adhesive.
And adhesive, exactly right. So when your people in your shop are putting these things together, you put a little bit of adhesive on the rubber, you put the catalyst on the nylon, then you stick them together, and if you get the rubber adhesive on the nylon, you won't get the bond.
Or vice versa.
Or vice versa, exactly right. You don't get the proper bond. That's not really difficult if you just pay attention to what you're doing there. There was something else I was going to say, it'll come back to me. But you're right, the adhesives on the rubber, the catalyst, I was going to say this. The common mistake made in splicing nylon core, and everybody knows, a belt is no better than the splice. If the splices don't hold, the belt's worthless. It's just not, it can't run, it's no good for anybody. So splicing is critical to belting. When the people do these kind of splices in the field and sometimes in the shop, if a little catalyst is good, then a whole bunch is really good. Absolutely wrong. The least amount of catalyst you can use is way, way better than more for a myriad of reasons. More catalyst means your cooking times or your curing times are way off. If you use too much, you may need 3 times the amount of time for that to set right. If you use too much and you put it together and you put it in a press, you get that thing wanting to push away from itself or turn sideways. If somebody is having trouble in the field with splices on nylon core in particular, go look at their equipment and look at their press. They'll have a waffle iron style of press somewhere in that plant. If there's glue all over that or catalyst all over that, they are for sure using way too much. You know exactly what the problem is when it comes to their splicing. The amount of catalyst that it takes, you would take an acid brush and cut it down so it was very stiff, and you would dip it, shake it off, dab it on the skive area, and then take a putty knife and scrape that off. I mean, it takes so very, very little to get a good splice. When you're analyzing failures on nylon core, most people use way too much adhesives when they do those splices, and they don't get a good bond.
You know what an acid brush is? It's a natural bristle. A natural bristle. So typically, it's going to be a metal holder wrapped around some natural bristle. You can't use polyester. You can't use polypropylene because the catalyst would likely melt what you were handling.
That's
so you
a good
use,
point.
horsehair, hog's hair, natural bristle, and like he says, you take it's not a very long bristle, but you can trim it just a little bit, and that'll make it much more stiff and rigid, and almost gives it an abrasive character to it, and you can kind of dab and spread it, and it'll tend to kind of rake it. You've laid tile, and you don't want a solid layer. You actually have grooves in it, and this will keep you from putting too much.
Mm-hmm. Very important not to use too much catalyst when you do this. But it always amazed me. I was talking about the line shaft in the paper mill and pulling 4,000 pounds on maybe a 6 or 8 inch wide belt. You're going to probably be exposing about, what would you say, Ron, maybe an inch and a half of nylon across that 8 inch wide belt, and that's all it takes to hold that belt together, and you're pulling on that thing 4,000 or 5,000 pounds. Nylon core splices can be amazingly strong. A nylon core splice, when done properly, can exceed the breaking strength of the belt itself. It can go up to 100, 110%, maybe even a little bit more when it's done properly. So nylon core is very, very strong. That's why they use it. That was the old-fashioned way of transmitting power way back before V-belts and things like that. So nylon core is very strong, very forgiving on shock loads. Let's see if I covered it all. They must match together. The match lines, you got to match that nylon up. Get as much nylon to nylon as you can get. The rubber covers are glued. The nylon is treated with a solvent to melt. We talked about that. You heat them up in a press, and then the pressure helps evaporate the solvents and everything, and gets those things to flow together, and then you get a good bond. When it comes to drive calculations, again, we talked about it earlier today. Getting the drive calculations and stuff, I think, is really important. A lot of folks would go through and say, oh, your nylon core is 3 millimeter thick. I got one that's 3 millimeter thick. It has rubber on the top. Here's what to get. If there is any product out there that is probably more sensitive to the drive calculations, it's in particular when you're transmitting power. And when you're using nylon core and you have to stretch it a certain amount to get it to pull the loads properly. So drive calculations are important. Every manufacturer out there that makes this stuff has engineers, they have manuals, fill in the blanks and all that kind of stuff when it comes to calculating the power requirements of the drive. And they can send you these forms. You can fill it all out. You can do it the math yourself, but it's much easier to call them up, give them the information they need, which may include things like if it's a hydraulic tensioner, the distance of the stroke and the diameter of the rod and things like that. They might need to know some of those little things. Most all of the major manufacturers would know how to calculate the drives and tell you what thickness to use, how wide, and all that kind of stuff. So best to call them. Most nylon comes about 12 to 13 inches wide. And some people will take that nylon and hook them together to get wider pieces. What do you suppose? 40 inches maybe max?
60? Yeah, I mean
78 and
when
3/4.
Yeah, I mean when you look
Those are
at a
big
paper
pieces.
mill, some of the paper
But
mill
it's-
drives
it's
are
in
absolutely
sections.
huge.
Yes.
Absolutely huge. Cone drives where you so that they track perfectly. You're not running flat pulleys. You're not running crown pulleys. You can't use crown
Can't
pulleys
use a crown pulley.
because it would tend to break it.
It'll fracture
so
the nylon.
do you know what I mean with a cone drive? You do know what cone drives are, okay? Because
I could draw you a picture if you don't.
yeah. So,
All right,
So-
somebody wants me to draw a picture. They're hard to imagine. Okay, let's see if I can do this. You got a pulley here, and then down the way somewhere, you got another pulley, and they're shaped somewhat like that. You put a belt on here, and they have these guidlers, idlers, or whatever you want to call it, these cans on either side of that belt. And when you move those cans, you force this belt to the high side or the low side of the pulleys, and that increases or decreases the speeds at which that belt travels. How's my drawing? Okay. So you take these cans, you move that belt one way or another, and you're going to increase or decrease the speed of the belt. That's what we call a cone drive. You typically see those cone drives in paper plants, paper mills.
yeah, they start slow and build speed and run really, really fast. A corrugator belt runs really, really fast. And the other thing is with this type of system, it tracks perfectly. This belt will not off track. If it's
The
done
angles
correctly.
offset each other, and it'll keep the belt pretty much where the cans put it. We talked about crown pulleys. I don't know, you guys might not know that, but you have a pulley. Sometimes you'll see that pulley with a crown. In other words, the outside isn't perfectly straight. That crown is used as a centering device for the most part to keep the belt running on the center of on the pulleys. You can't use a crown pulley as a tracking device for nylon core. That crown will fracture the nylon. It won't work. It'll destroy the belt. So
One thing, when you calculate the drives for these, you use the neutral axis of the belt. Typically what we do on any kind of conveyor belt, we take steel tape and we measure the net endless length. And that's based on the surface at at the running surface, around the head and tail, and whatever else. When you're doing drives, you actually use the neutral axis, which is different, and you have to consider the total thickness of the belt, and there's calculations to do that. Yeah, how many people sell V-belts? A lot of you sell V-belts. You already know when you sell a V-belt, you've got the OD and you've got the pitch diameter. Same thing. So there's a neutral axis here on this nylon core belt. It's not the same as the surface. It's a neutral axis and it's a different dimension.
We're going to talk about plastic modular. We talked at the beginning of this morning about an extrusion for plastic, all plastic belt that's run through an extrusion head. Plastic modular is injection molded. Now we take a big press, if you will, put a die in here, and we drop links out of it that are then put together, assembled to make a belt. So if you take something like this is a 6-inch link. To make a 6-inch wide belt, it's very simple. You just put 2 links together and continue on to build whatever length you want. If you go do something different, then they do what they call brick lay. And a brick lay looks something like this. We've got 2 smaller modules put together with a bigger module, and you just continue to do that all the way out until you finish up with whatever length you want to do. You can build this out to very wide widths. If you want to go out to something like a 158-inch wide belt for whatever reason, you can do it with that. Okay, so that's what this is all set up as. This was designed and started out back about 40 years ago because a conveyor manufacturer couldn't find a belt of any kind, description, or whatever that would satisfy their needs for the conveyors that they were making. And that's how it got started. They came up with this idea. We just take some plastic pieces, put it together, and off we go. And since then, it has expanded into multiple manufacturers, multiple different styles and types, and a whole bunch of different variations. It is done in straight running, which is mostly what this is, so it's just going to go straight down to the end and stop, just like we are used to with a fabric belt. It is also done in radius, so it'll go around a curve. It'll condense on the inside as it goes around the curve, open up on the outside, and when it comes out, it opens itself back up and runs straight again. So now instead of having to have a transfer where that flat belt stopped onto a curved section, onto another transfer, and onto a straight section, you can run one belt around the whole mess. Now there's a lot of engineering that goes in here as far as turn radiuses and all these other things that are involved, but that in essence is what it is. Why do we use it? Well, first of all, it's positive drive. We have talked numerous times with the word stretch as it relates to nylon core belt, fabric belt, etc. So you run it under tension. All fabric belt is tension driven. This is not. We take a sprocket or a series of sprockets, put it in underneath. There will be defined sprocket paths in some cases and others not. And we sprocket drive it. We talked about catenary sag a little while earlier. It was brought up, you sag this, let it drop down off the pulley. So we're not wrapping 180 degrees. So we allow this to disengage the teeth, come down, sag a little bit, and then come back up, and that's how it runs relatively loose. All right? Everybody understand what we're talking about? Okay. It's relatively easy to put together. Okay. I have one up here someplace. I mean, basically what you're going to do is you're going to take sections and you're going to put a pin in it. It doesn't get much easier than that. You don't need equipment. You don't need presses. You don't need finger punching tools. You don't need anything else. Put the pin in it, make sure it's locked in place, and off you go. From a maintenance standpoint, it's simple, it's easy, it's a piece of cake. From a cleaning and sanitation standpoint, so-so. Much easier to repair because we can pop that pin out, take out whatever rows of modules that are damaged, broken, torn, whatever the case may be, put another section in, drop the pin back in, and off we go. So you're up and running. You don't have to worry about coming in with a piece of material and putting a Dutchman in it, which is a short piece to take the place of the damaged section or what have you. And you're back up and running again with it real quick. Positive tracking, it's going to run, as long as that conveyor is straight and lined up, and the sprockets are all in line, it's not going to track off. The teeth are positively engaged. It's going to run it straight and true. When it goes around the curve, it's going to keep it all in line. You don't have to worry about putting any type of chain or grommets or any other hardware on the outside edge, what you do with a fabric belt to keep it lined up. And then the key reason they did this is because if you look at this, there's a lot of open area in here. And it comes in different variations of open area. There will be on all the data for this, it will tell you a percentage of open area. So you know how much airflow is going through here. You know how much water you can push through. That was done for drainage. We can run water on here, and no matter how many holes or how much open we haven't done anything to damage or decrease the amount of pull that this belt can take. Because we didn't do anything to it. Unlike a fabric belt, when you perforate it, put a hole in it, you're going to lose some strength. With this, you don't. We're driving off the hinges, so everything will run nice and true. I'm going to start some of these samples around so you can take a look at them, play with them, or whatever you want to do with them. From a drainage standpoint or airflow, you can get something wide open like this one here, which is side flexing, which has to be open, or a straight running version like this, so that you get plenty of flow through here. And it doesn't matter whether it's, water you're trying to run through, if you're trying to dry something or whatever the case may be, all the open variations are there. We talked about curves and so forth and so on. From a fabric standpoint, and all the fabric guys will tell you this has not been kind to the fabric guys. And the reason being is it lasts so long. For most fabric guys, you want that repeat business. You want to be able to get that belt sold, and if it lasts 6 months, great. I know I'm going to get another order in 6 months. When you talk about modular, you're talking about years before you may have to go in there and replace a belt.
You just hope their maintenance is lousy and they break a bunch of modules.
But even when they break a bunch of modules, all they're going to do is they're going to buy a few modules to repair it and keep that same belt running.
Yeah.
There are belts in operation out here that we have seen, modular, that have been on for 20 years, and all they do is they replace a section and another section and another section, but the same basic belt is there. It doesn't change. So that's the downside. The upside is it does solve some of the other problems that you run into from a tracking standpoint, from a positive drive. It doesn't stretch. It's easy to put together, and all these other things. Okay? There are 4 primary compounds that you will run into. Acetyl, acetyl, however you prefer to say it. You will see it referred to today as POM, which is the chemical name polyoxymethylene. You don't have to write that down. You can just write down POM if you want. That's the easy way to do it. Polyoxymethylene is the most common. It has the broadest range as far as temperature variations are concerned. You can get down to about -40. You can get up to 194 or so. We will tell you to be very cautious when you use this at the low end, because if you stop it in a freezer or something, it will get brittle. Even though it's rated down for -40, if you're down in that -20 range or below, it does get brittle if it sits stationary for the weekend. Second thing with acetyl is it's the strongest of the materials. So if you're looking for something that's going to give you the best load carrying characteristics and everything else, acetyl's the way to go. Polypropylene, where you need something that's going to give you some higher temperature ranges, polypropylene will do that. This is used, generally speaking, where you've got hotter product or you're running in a warmer atmosphere, because it'll take up to 219 degrees Fahrenheit, but the low end scale is only 35, and that's on the positive side. You really want to kind of keep polypropylene above 40 for the most case, because even though it says -35, it's okay. When you get below 40, it starts to get brittle and hard. Polyethylene goes the other way. Oh, strength-wise, polypropylene generally, unless you put adders in it, is about half the strength of acetyl. Polypropylene Also gives you one other thing, very good chemical resistance. So if you've got a lot of chemicals or anything else in there, that's the thing to use. Polyethylene, good cut resistance, not as strong as the other two. Takes the low end temperature. So if you're running freezer discharges or in a freezer or in cold rooms or what have you, polyethylene is the compound you want to use here. It will take down most cases to about minus 60 Fahrenheit.
What was its top end again?
Polyethylene top ends out at about 165. And then, if you want to get into something for higher temperatures, you can do something in a nylon. This happens to be a nylon, as you can see, very open. This is something you'll see in applications like shrink tunnels and so forth, where the temperature is about 300 degrees Fahrenheit. There are 3 different variations of nylon that are out there. Each one takes a different high-end temperature. You can get a plain nylon, you can get a glass reinforced nylon, and you can get one other nylon variation, a PA66. Top end temperatures will vary from about 248 up to 350 degrees. Now when you do that, if you're going to run high temp, you need to make sure that the pin material that is used to put these together is the same basic material as the belt. You can't use a polypropylene pin in a nylon belt and expect it to hold up to 300 degrees because it won't do it. Polypropylene won't take that. So they use a nylon pin. They use polypropylene pins. Some of them will use acetyl. We don't recommend acetyl normally because it doesn't have the good wear characteristics as a pin material that it does as a belt. But those are the different variations as far as compounds. There's some other ones, some specialty ones. I'm not going to waste the time talking about those. Pitches. How do we measure the pitch? Center of pin to center of pin. This isn't a good example because it's side flexing, but on a straight running belt, if you look center of pin to center of pin, this would be 1 inch. That wasn't that hard, was it? So that's how the pitches are measured. You go down to a 1/2 inch pitch is generally the smallest. This happens to be a 1/2 inch pitch version. This will get you around much smaller sprockets. You can even run this around a nose bar or a nose roller. We recommend roller because it reduces the amount of drag as it comes around that transfer point. One of the other things, talk to the manufacturers, but they will generally tell you that the diameter of that nose roller should be at least 1/8 inch more than the pitch of the belt. And the reason is it will make a smoother transfer and you don't get the noise. One of the downsides to modular is noise, because it will click, clack, and what have you.
There is a great advantage to doing close transfers, though, with the modular belt. It will work in that way. You'll see some pictures later of that. The other thing that I wanted to mention when we were talking about widths, talk about the nominal width and the actual width.
Nominal width, unlike fabric belt where you can take a big roll and you slit it down, and if somebody says they want a 24-inch belt, you get a 24-inch belt, assuming the guy that's slitting it is paying attention to what he's doing. Now you can cut this if you want to cut it down to get some oddball width, but it's generally done with a bandsaw and it doesn't leave you the best edge out here. So what you're going to go with is whatever the actual width. Most of the manufacturers will tell you what that is. If you order a 36-inch wide belt in polypropylene, the actual width is going to be 35 5/8. And it depends on the manufacturers, because the manufacturer's tooling is done differently.
This becomes critical if you're putting a modular belt into a pan, that you don't have it messed up, because the pan is only so wide. You best not try and put a too wide a modular belt in that, or it won't fit.
So those are the differences as far as pitch variations are concerned. And come back to sprockets in a minute. Let's talk about some of the other variations you can get. When it first came out, it was used in the food industry primarily. And this took a lot of rubber belt out of the mix because it was so much easier to take care of. It was easy to drive. You didn't have the stretch problems. You didn't have strings coming off or anything else. So the food industry was the first place they went. Today, because you see some of it being replaced in the food industry, they have moved into a variety of other applications that you wouldn't necessarily think about for modular belt. Warehouses. Why would you put modular belt in there and you take a 2-ply black inexpensive rough top? Because now you can put a rubber top on here, get it to haul stuff up an incline, and instead of replacing that rubber belt every 6, 7, 8 months or what have you, and having rubber dust build up and everything else, you can put this puppy on there and it'll last for years. You don't have to put them on every module. You can separate them. So you can center them if you want to do that. And it comes in a couple of different variations as far as this one here is actually raised in the center as opposed to totally flat. It does not lift out, lift off. If you want to put cleats on it, you can put cleats on it. This has a little bitty cleat on here. We don't have side walls. And by the way, in the plastic modular industry, these are called product supports. They don't call them cleats. They also have side walls or side guards in the case of modular. So instead of the corrugated sidewall that Roy was talking about yesterday, we now have side guards. And if you look at this when it comes around, you'll see what they do is they actually knock a hinge out of the base module because the side guard has its own hinge. And the side guard drops in where they've knocked that hinge out of place. If you want to do something that's not a smooth surface, we want to break the surface contact area up, there are ones that are made with a texture top on it so that we can get better release, etc. And we were talking about accumulation earlier and transfers. They have what they call a raised rib. Raised rib is just what it says. It'll have finger combs that come in here, so when it goes over the transfer plates, it slides right off nice and smooth and there's no gap. And then when you're handling, if I may borrow this, when you're handling stuff like this, it transfers nice and easy. We talked yesterday, I believe, about how thin the walls are on this. I mean, there's almost no plastic in this anymore. You start accumulating something like this, and you can have some major problems as far as collapse of the container, especially if it's empty. So they'll use things like this, or this particular case, this is acetyl with a low friction ingredient added into it. Generally, either a Teflon or a silicone adder in here to reduce the friction between not only the belt and whatever support system is in place, but between the belt and the containers that you're carrying. So that's raised rib. And if you don't like a straight cleat and you want something that's going to give you a little more capacity going up the hill, you can get something like this that almost forms its own little bucket, if you will, to hold product in here as you run at very steep angles. Okay? Sprockets. All of these run sprockets, obviously. Sprockets, the general rule of thumb for spacing of sprockets is 1 every 6 inches plus 1. Okay? 1 every 6 inches of width plus 1. So if you have a 24-inch wide belt, that's going to be how many? 5.
What was that again, please? General spacing rule.
One general spacing rule is 1 every 6 inches of width plus 1
For the drive sprocket.
for the drive sprockets. So if you have a 12-inch wide belt, how many sprockets? 3. I'm trying to keep these real simple numbers. Okay? That's the rule for sprockets. Now, if you have heavy loads, long runs, or anything like that, then you may increase the number of sprockets that are on here. You may do 1 every 3 inches or 1 every 4 inches. Most of the manufacturers will tell you they would like to see an odd number of sprockets on here, so you can have one in the center, which is either pinned to the drive shaft or has locking collars on either side so that it can't move too far. The rest can free float. When you get out here to the outside edge, they'll usually recommend that you're inset a half to 1 inch from the edge with a locking collar on the outside, so again that outside sprocket can't walk out and walk off. These things are running loose, they tend to move. Do they stretch? They can. Does material move? Absolutely.
A PU timing belt.
You can use them for reciprocating applications where you have a plane and you go left or right or forward and reverse, and the two ends are tied or fixed,
Right.
and you have a pulley that's driving it in the middle. Typically these would be flanged drives, and you can index it with a synchronous drive. You can do it to precise dimensions with servos, so you can take it from one position to here, to here, to here, and then return back, things of this nature. Quite simply, fixed ends, not concerned with pulley diameters or anything like that.
No, it can be operated both ways.
Yeah,
It can
forward,
be
reverse.
forward or reverse. It doesn't have to be joined together. That's an excellent point. A lot of times mechanically they'll be joined together as well. Mechanical fasteners as opposed to any type of fusing.
Starting and stopping and indexing.
Yes,
Index.
precise
Index.
stopping and starting.
Electronics industries where they might be etching a transistor or doing something where they need to stop on the dime and know that product's where it's at. You see a lot of them with perforations and things like that for vacuum, rubber covers.
Yes.
But you can run them with, you can use synchronous servo type drives, so they have stepper motors and they're very, very precise. You get very, very precise locations.
Positioning in a product, a positioning of a product in the process. The tensile strength of the carrying member is either going to be of stainless or Kevlar. You don't see the word fiberglass up there, do you? Fiberglass is used a lot in synchronous cog type power transmission belt. So stainless is used so it is very strong. Kevlar is your synthetic that is equally as strong. It's brittle and it doesn't like shock loads, right? You don't have that on a power transmission belt that's this type of unit, a PU timing belt. Stainless steel is the same way. Stainless steel doesn't like shock loads either. It's extremely strong, but it's not a product that likes shock loads. I'm going to pass around just some cards that show the different types of product that is being used. The pitches that are available are both in metric and imperial. The metric, of course, is like T2.5, that's millimeters, to T20, okay? Those are the various types of timing belts. The imperial size is like the standard timing belts that are used as synchronous cog belts, anywhere from the XL pitch up to the XH pitch. Included in that would be an H pitch, which is the ½ inch in between there, okay? So you've got this whole gamut of particular products that use a sprocket that's like the power transmission synchronous cog belt, but it is simply going to be used to carry the load, not for extreme tensioning. The width limitation. There's a maximum width of 18 inches without using a longitudinal splice. Now you can slit this material, it's slittable. You can buy it in various widths or get a maximum width of 18 and then start slitting it down to the widths you need. But it's a little different way of joining the product than you would a conveyor belt, because you do have the tensile member in there that's stainless steel or Kevlar. You have to strip that out, and you have to have a mold to place it in to retain the pitch. And as you strip out those cords, you lay them side by side, or you butt them. But that's because you're not doing it for power transmission purposes. The nomenclature, what do you suppose we have here? 100 millimeter, T20. Okay, that's your 20 millimeter pitch, and 8,000 length. It's done the same way as power transmission. The bottom one is now 1020. Okay, what do you think that is? It's 102 inches long.
Okay.
Just put a decimal point in front of the 0.
Okay.
The H tells you the style of pitch, and 50 is the half inch. 75 would be 3/4, 100 would be 1 inch, 150, inch and a half, 300. It could be any number of these back here for the width of that, okay? Now, got the word accessories. You can use this to move material. You can place on it cleats. We talked about cleats yesterday. You can put a lug on it. They can be of various shapes. The guides, they can have a guide on them. Sometimes you'll have a groove out of the tooth profile to help align it, to keep it in line if it's critical. They come with nylon covering on the tooth side. The nylon covering on the tooth side adds to its wearability. It resists the abrasion that it would see otherwise running over the sprockets. And you can put special covers on top of that timing belt. But again, it has to be compatible with the polyurethane.
High temperature belts come in several different forms. I do have some samples here which we'll pass around. Just start this one and moving around. This is a fiberglass fabric, and it's been impregnated with Teflon. These comes in different weaves. They come in different plies. You can actually have multiply. And the coarseness or lack of coarseness in the weave will vary, but it's all Teflon coated fabric, and you can tell it's relatively stiff. So you don't really go under real small pulleys with this type of product. You're trying to take advantage of two things. One is you're trying to take advantage of the fiberglass or the Kevlar for the temperature capability. The other thing you're trying to do is take advantage of Teflon or silicone. Now, these are used for, many of you have on t-shirts that are printed. They probably went through a tunnel that dried them. These belts typically are a little bit wider, a little bit longer. They're relatively supported, but you've got this air movement. A lot of these belts are open mesh, fairly open, 1/4 inch, even bigger, so that you get a lot of airflow through there. Decorating of plastics, a lot of other things, you will see this type of product used. And oftentimes they are they will have their edges sealed, especially the open mesh material. The open mesh material will actually take some of this thinner material and they will bind it about an inch in, top and bottom, on both sides, and the ends will also be built up because this is fairly thin material. There are 2 to 3 different ways you can join these so that you can have them. They're not used endless. They're always joined in some way mechanically with lap splices or loop type splices, where it's actually the same material here that was the base material, or they use this binder to make it thicker, and then they use mechanical fasteners lacing, typically the hammer-in common bar type lace. So this is one form. These are a little thicker, a little bit heavier weave. You can see them. And then we get into some of the silicone type products. The advantage of silicone is that it's somewhat more flexible, and with the flexibility of the silicone, you can do a lot of different things. The release characteristics are different. You can have a little bit more of a cushion effect. Notice these grommets here on the side. They'll use them sometimes to drive the belt or to keep it from tracking true. This picture shows actually the process where they're actually doing the impregnation. And this application here shows a belt that would be run in a plant where they're using it for some production process.
That's if I'm not mistaken, that's like a cooling table for rubber.
Okay. So there's a lot of different varieties, different colors, and different thicknesses. Here's a 2-ply, and this one is actually a 3-ply. The Teflon coated fiberglass, you don't usually build up in plies. The silicones, you do. Silicone is a rubber form, a type of rubber, and you can do a lot of things with it. Interestingly, we know that stuff doesn't adhere very well to silicone, and yet it can be laminated, and you can have multi-plies so that you get the effect. Again, notice that these are fairly rigid type products. You have very generous pulley diameters, and you want to maintain those large pulley diameters so that you get good characteristics for total life. It's a very common product, very widely used. Everything from many different kinds of food to printing to anything that needs some temperature, but oftentimes it doesn't have much physical mechanical support. So these are fairly loosely woven products, and so you'll use drives and support mechanisms such as the grommets. And you have to be careful with the type of lagging or something like that you would use, so you do not prick and tear these fibers and these fabrics because they can be fairly fragile. Here we can go down with the silicone type products into the -100 degrees Fahrenheit. So their cooling is the primary consideration. And we go all the way up into the 600 numbers. 600 from a process heat point of view is a good number. There are a lot of things that need to travel relatively slow over time, so you get some process to occur where you need time and temperature, but you don't need pressure. So this is where you would use this type of oven or Lear or drying oven, different names, different applications, different industries. The fabric pin splice is commonly used on both styles, and those are fabricated by the belt manufacturers. I don't know if any of you have capability to do that type of fabrication, do you? For you to do a lap or a loop type splice, you don't have a way to bond that together. Those presses are quite a bit different from your presses. The temperatures that they work at this would be somewhat higher. They're not high pressure, but the temperatures are somewhat higher. So typically the manufacturers would produce that type of lap or loop type splice. Sometimes they use wire type splices where they actually sew in a wire loop reminiscent of the spiral type lace, where it's a loop type spiral, and they'll sew it on both ends and then use a metal pin to bind it. Metal fasteners are common. Wire hooks are not particularly common for this. Wire hooks tend to go in, and these type of fabrics, being wide open, widely spaced, not much in the weft, mostly in the warp, don't have much pull-out resistance. Common bar type lacing typically works better.